Okay, so good morning, everybody. Welcome to this month's session of the Darboux seminar. We're very happy to have Elba Garcia-Failde, who's local, so Université, and she'll be telling us about topological recursion.
Thank you for the introduction, and thank you also for the invitation to speak in this nice seminar. So in this talk, I will be introducing this procedure called topological recursion that maybe you already heard about. And I will be talking about the particular problem of quantization of spectral curves. Oh, maybe I should not move too much. Okay, so this is my plan. The first point is really very introductory, and it's where I want to spend quite some time. So in total, I have more or less an hour and 15. Thank you. Okay, so I will try to spend quite some time in the introduction, and then we will go deep in the details of how to quantize spectral curves in a very general setup. So I will start by introducing what is this topological recursion. Then we will see some more details, but at least here you can see the idea. So topological recursion was introduced by Chekhov and Eynard around 2004 in the context of large size random matrices. And then it was upgraded to a universal theory a bit later by Eynard and Orantin in 2007. And it's a procedure that works in a very, very general context. That's what I said. That's why I said that it was promoted to a universal theory. So in general, what is our goal? So you have an idea of what we do in general. This needs to be made precise for every problem. But what we do is count surfaces that I call here SGN of a certain topology. So GN, some genus and N boundaries for mark points. And the way to do this is topological recursion associates to some initial data called the spectral curve, a family of differential forms indexed in GNN. And we found this for all GNN, just started from disks and cylinders. Probably this audience here already heard about matrix models and these kind of things. So this has to do with the topology of disks, and this has to do with the topology of cylinders. So this has to do with the spectral curve of the matrix model. And then like this, we can produce all the correlators, for example, of the matrix model or of other types of problems. So, okay, I will say a bit more details about what is this spectral curve. So the spectral curve consists of a Riemann surface that I call sigma, and then a ramified cover, so a x, which is just a meromorphic function from this Riemann surface to CP1. So we can see the Riemann surface and we can see it as a realization of a ramified cover of CP1. And then we take a one form and a B differential. So this is the one form and the B differential. And we build this one form out of two functions, so out of the x and the y. Usually we just take y dx. And then the B differential, well, we'll see here what are the properties. And then we build by recursion on just this quantity, 2g minus 2 plus n. So some kind of measure of the complexity of the topology of the surfaces of the problem that we are solving. We build the whole family for any GNN. So, okay, a bit more details about how this X has to be. So X will have simple ramification points. So they are just, you can just think that they are just the zeros of the X. They can also be infinities that are ramified and then they are defined differently. But the ones that play a role, an important role in topological recursion are just the finite ones. So they're just the zeros of the X. And we have to suppose, I mean, I'm presenting for the moment the simplest setting of topological recursion. Then there are many generalizations. But here we just have to take Y, which is holomorphic around the ramification points of X. And this will tell us that locally, this looks like a square root. So we have a local involution that exchanges the two sheets of the ramified cover. around every ramification point. So it may be that this exchange of sheets is just local. Then we need all these ingredients in the formula.
CR of X is for critical point of X.
Exactly, yes. So this is my notation for the ramification points here. So, yeah.
What are Y and X here?
Sorry?
What are Y and X?
Y and X, they are just meromorphic functions from the Riemann surface to CP1. That's it. And then, well, X, you can see it as a ramified cover of CP1, and it has ramification points, which are the zeros of dx, and they are the critical points. Okay. More questions about the setting? And then we take the bidifferential. Maybe I didn't emphasize enough, but these differential forms that we built, including, of course, the initial ones, they all live on the Riemann surface. So all these coordinates, they live on the Riemann surface. Okay, so the bidifferential also lives on the product of the curve, and it has double pole along the diagonal. So it has a pole structure that looks like this. And then the rest has to be holomorphic. Okay, in particular, if our spectral curve, so our Riemann surface is of genus 0, then most of the time our holomorphic part will just be 0. You will see later why. There are some choices to make, but yeah. I don't know if I can get rid of this bar. Probably not. So we will have to adapt it. Let's see. Yeah, so here you can see how it works, the formula of the topological recursion. So I'm giving you a picture, so it's a bit easier to remember the structure. So we associate to every differential indexed by G and N a surface of genus G with N marked points. And then I decorate these N marked points with Z1 up to Zn. And then we can express the topology Gn in terms of lower topologies. This is the idea, and this is why it's called topological recursion. Remember that it's a recursion on this quantity over here. So it starts from the simplest topologies and it builds more complicated topologies.
There's some symmetry property for omega Gn.
Exactly, yes. The omega Gns have many nice properties, and a very fundamental one is that they are symmetric. Otherwise, the definition already doesn't make sense. So the way to build these differentials is just summing over all ramification points of X. That's why I talked about them here, because they are really important in the formula. And then we just take residues on these ramification points of a certain, with respect to a certain variable that you will see how it arises. So this is the kernel of the recursion that you will not see, but you can just build it from omega 0,1 and omega 0,2. So you can believe me that it's an easy expression. And we denote it just like this, with a trivalent vertex that also represents a pair of pens. So a way to imagine this formula is just the way of cutting a pair of pens out of this surface, in which the first surface of the first boundary of the pair of pens corresponds to the first boundary here, in all possible ways. So one possibility is that we cut this pair of pens and then we get something that is connected, or that we cut it in all possible ways to get something disconnected. So in here you see the kernel, and you see here the topology G-1, because we have lost one hole, and we have gained one insertion. So we have, that's why we have here n+1, and here you have to put Z and the involution with respect to the ramification point evaluated at Z. Then just Z2, Zn. And here we just do the same. This is the kernel times the differential associated to the surface times the differential associated to the surface, in which in this boundary insertion, we just put Z, and in the other one, we just put sigma A of Z. Okay. Are there questions about the structure of the formula? Of course, you cannot get all the details, but
There is something quite strange for me, because the evolution seems to be linked to a particle a particular Riemann surface, and then you put sigma in a surface of genus sigma -1, which cannot be the Partition curve.
Exactly. So this is an important remark. The surface that we start with has nothing to do with the surfaces of the problem that we are working on. The SGNs, for the moment, I didn't tell you anything about their structure. In general, very often we are solving problems on a surface of genus G and mark points. But in general, they have nothing to do with the sigma that we start with. And we don't know anything in general. Then concretely, these sometimes are just topological surfaces and we are counting graphs on them. Sometimes they are Riemann surfaces and then we are computing volumes on them. So they can have different structures.
I'm sorry, in the pink or whatever color surface that you draw is sigma or is something else?
No.
It's not. It's just a picture.
Yeah, this is just a graphical representation to help you remember how the formula of the topological recursion works. And these surfaces that I'm drawing have to do with the SGNs of the problem. Yes.
So in the context of topological strings, should we think about sigma as kind of the mirror curve and these purple surfaces, the world sheets that
Yeah.
generate, and the relation is the holomorphic Elba equation?
Yes, for example, you can think of that setting. You will see in a moment some examples.
The insertion points Zi are on the mirror curve. They are not on the world sheet.
Yes, they live on the sigma, the ZIs. They are coordinates. So remember that we are building differentials on the initial sigma. So we have an initial sigma where everything lives. And then we have the surfaces of the problem that we are solving. But I think it should correspond.
It's consistent, right? The insertions on the world sheet correspond to the points on the mirror curve.
Okay, let's maybe continue and see some examples that will help you imagine how this works, depending on what you know. So I see topological recursion as something that really nowadays helps us connect different worlds. So here I put some of my favorite and also the ones that are more involved. I mean, my work is more involved with these topics. So in here I put combinatorial maps. By that I just mean surfaces with graphs embedded on them. So topological recursion can help us count them, so can help us with combinatorics, and also can help us compute quantities that are important in probability. In here, I just put the modular space of curves, because very often we just compute intersection numbers on MG and bar. If you don't know much about this, I will tell you in a second. Then there is also a relation to integrability that this talk will be about. And this relation is still being built, so maybe the arrows should be dashed. But we expect also to be a resurgent version of topological recursion, and we expect it to be related to each of the vertices, in case someone is interested in that. So, okay, here are some examples, so we can comment some settings that maybe are familiar to you. So first of all, the omega GNs have nice properties. So as you asked before, they are symmetric. They have poles at ramification points, so we can control all their structure. They also have controlled deformations along families of spectral curves. These will also play an important role in the talk. And then they also have several properties like the dilaton equations, symplectic invariance, loop equations, modularity, integrability. Okay. So just to give you a very particular example, if you have this relation between X and Y, this will build for us a Riemann surface. Or yeah, you can think of this as a complex curve or as a Riemann surface. This is the so-called Lambert curve. In that case, topological recursion computes Hurwitz numbers. Hurwitz numbers, they are just counting coverings of the sphere. Then if you take this other relation, so okay, I have to warn you maybe that these are not the simplest spectral curves. First of all, they are not algebraic. You will see some in some details some algebraic curves later. But here is to give some nice examples. Maybe you know these problems. So in this case, topological recursion just computes for you Mirzakhani's volume. So Mirzakhani found this recursion among volumes of hyperbolic surfaces, of modular spaces of hyperbolic surfaces. And topological recursion reproduces Mirzakhani's recursion. And then you can also imagine it a bit on the more on what you were saying. Topological recursion on a mirror curve of a toric Calabi-Yau threefold computes its open Gromov-Witten theory. Well, it's also related to Chern-Simons theory, to some statistical physics model. Actually, the beginning of topological recursion, it was actually introduced to solve the one Hermitian matrix model. Nowadays you can solve many other things. You can also solve the Ising model, the Potts model, the Owen model. Then it's also related in a very general way and in a very useful way to what is called semi-simple cohomological field theories. If you haven't heard about this, don't worry. It's just a way to collect important classes on modular spaces of curves. Then it's also related to reconstructing WKB expansions that you will see in this talk, and integrability, isomonodromic systems. And conjecturally, it's also related to knot invariance. And well, nowadays it's work in progress to also give a non-perturbative version of this topological recursion.
What do you mean that you can use it to solve the Ising model in this context? For what? For doing to what?
Yes, so if you imagine the Ising model, the way I think of it is just you take a surface of genus 0 with some graph on it, and then you have spins that can be positive or negative, and then you have to solve the topology of the disk and of the cylinders. So you know how to do it for the planar case.
So the idea is to solve the Ising model on Riemann surfaces of high genus.
Exactly. Yes, this is what I mean.
Okay.
Yeah. Are there more questions here? Okay, so this is all a bit vague, but now you will see an example that should give you a more concrete idea. So I will do with a bit more detail the case of Witten-Kontsevich, because it's just the most, this is really the easiest spectral curve that you can have, solving a very interesting problem. And it's a case in which we really know everything. So it can help us model all these connections that I was talking about. So I want to say some words on the modular space of curves. So here I just take the modular space of curves MGN. So they are just smooth curves of genus G with n mark points up to some conformal reparametrization. And I want to consider the Delignon-Mumford compactification. So for that, we just need to consider, so to compactify this space, we just need to consider certain singularities on our surfaces, in particular, just these nodal singularities that look like that. Okay, so in here, let me just introduce these very fundamental classes. In MGN, for every point in MGN, we have a curve with its n mark points, and above it, it sits, the surfaces actually sits, and we have the n mark points. So for example, if we take the ith mark point and we take the cotangent space at that point, here I wrote that as the tangent, but okay, it's just to give an idea. And then we make this point in the base vary, then the surface will vary. And then if we consider how this bundle, how this space varies, well, we actually have a bundle, which is Li. And since we have n of these mark points, we have n line bundles that are very natural. And if we consider the first Chern class, that is just a cohomology class in H2, well, these are the so-called psi classes. And probably you heard about Witten's conjecture, in which he computed the intersection numbers of these psi classes. So they are just integrals over mgn of these psi classes. These numbers will be 0 unless this has top dimension. So this has the dimension of mgn. So this has to be 3g minus 3 plus n, otherwise it's 0. And in general, it's a rational number. And these numbers are really important because they give us important geometric information on mgn. So, okay, this is one of the big motivations to work on topological recursion. To compute these cohomologies is really, really complicated. There are many mathematicians working on it. And one way to obtain geometric information about this mgn is to compute these numbers, for example. So mathematicians knew how to do that for low topologies. And then you probably know that we then conjecture that you can compute all these numbers recursively. Just here you have the generating series of these intersection numbers of these psi classes. And Witten's conjecture tells you that this series satisfies the Korteweg-de Vries hierarchy, so the KdV integrable hierarchy. This is the first equation of this hierarchy. And what I mean is just that for this particular equation, it's just that if you take the second derivative with respect to the first time, so the 0th time, if you take this second derivative, then this will just solve the KdV equation. And of course, to determine f uniquely, you also need the string equation, which is some kind of initial condition. Well, it's exactly the initial condition. So, okay, two nice things. Well, Witten's motivation to state this conjecture was that two different models of 2D quantum gravity had to coincide. So one is the one in which you just model surfaces. So you just discretize surfaces with a triangulation, and then you send the number of vertices to infinity. And that is known to satisfy the KdV hierarchy. And on the other hand, you get something up to conformal parametrization, and then you get the relation to the previous setting. So that was why we then thought this should be true. And this was amazing for mathematicians because this allowed to compute all these numbers recursively that otherwise were very, very difficult to compute. Okay, and what is the relation to topological recursion? Well, here I just gave an explicit version of Witten's conjecture. So this is the formulation using Virasoro constraints. So in case you want to compute intersection numbers, here you have really everything you need. So this is an equivalent way of stating Witten's conjecture. You just take these Virasoro operators that they are indexed from -1 on, and they satisfy the Virasoro relations. We know that these operators annihilate the partition function. And that's equivalent to Witten's conjecture. Okay, so just to summarize the logic and to put topological recursion in the picture, in 1990, Witten formulated his conjecture that the generating series of intersection numbers satisfy the KdV hierarchy. And then just 1 year later, Kontsevich introduced some combinatorial maps. So cell decomposition of the modular space of curves, actually. And he was able to relate them to a matrix model in a kind of standard way for physicists, but not so well known for mathematicians at the time. Then he was able to relate the matrix model to the integrable hierarchy, also using works of other people. And the really amazing thing he did is he managed to build a combinatorial model using these combinatorial maps for the psi classes. Really, for each geometric class, he built a combinatorial model, and then he had a way to relate this to the integrable hierarchy, and like that, he gave the proof of Witten's conjecture. Okay, and nowadays in this problem, we know how to relate everything to topological recursion. It also helps that it was a well-understood problem before topological recursion. So now we know we are able to relate each arrow to topological recursion. So what is exactly the relation? So if you take the Airy spectral curve, that's the name we give. So you take just X, so we take the Riemann surface, the initial Riemann surface will just be CP1, so genus 0. And then x is just this function over here, z2 over 2, z2 square over 2. So the ramification point will just be 0. So if you take the derivative, you compute the 0, it's just 0. And then y is just z. This is what we call the Airy curve. You will see y. And if you run the topological recursion on this curve, this is really all the data you need. The omega GMs will produce for you these numbers recursively. And this recursion is actually equivalent to Witten's conjecture. Okay. So now I want to give, so through this arrow, you see already the connection to integrability, which is the part that I want to focus on in the talk. And in particular, it will be connected to differential equations. How exactly? So, okay, we consider the Airy function, which is just the solution to this differential equation, this linear differential equation of order 2. And then we know that it has an asymptotic expansion when lambda goes to infinity of this form, in which you can actually see that these guys over here, they are generating series of intersection numbers themselves.
So it's an extension at small lambda, at large lambda.
At large lambda, yes. So you just take lambda real, and you take large lambda, and then it has this property. If you expand it in some other sector, because of course this function jumps, if you expand it in some other sector, you will get other numbers. And they are related, of course. So if we want to keep track of the Euler characteristic of the surfaces of this problem, we can actually introduce a formal parameter h bar. This is my way of imagining why we introduce h bar, but probably you see other reasons, because this is supposed to be the quantization. So we just introduce the parameter h bar through a rescaling of lambda. And then we just obtain the wave function associated to the Kontsevich problem. So just the Airy function scaled like that. And then this satisfies this equation over here, which admits an asymptotic expansion of this form. And you can see that h bar just keeps track of the Euler characteristic. So this is just the Euler characteristic of these topologies that are in here. Okay, and then the relation to topological recursion is that if you apply topological recursion to the Airy spectral curve, it will compute for you both the partition function and the wave function. And also the quantum curve, so this quantum curve over here, can be constructed out of topological recursion. So the question is this a general phenomenon? This is what we will focus on this talk. So now I want to present what I mean by quantum curves in the talk. So here I'm just taking a polynomial. So it's a plane curve, and our Riemann surface will just be built out of this polynomial. You see that we are simplifying a bit the setting that I gave at the beginning in some sense, and in some sense we will make it more complicated. But the simplification is that here we will just consider algebraic curves. So that's why I'm saying this is just a polynomial. And the zeros of this polynomial just built for you the Riemann surface. And in this case, the Riemann surface can have any genus. You will see why this plays an important role in this problem. So we call a quantization of our plane curve a differential operator, which is of this form. So now we denote x hat just multiplication by hat, so it's the operator multiplied by x, and y hat is just the operator differentiate with respect to x and multiplied by h bar. Okay, and we want to call this a quantization of this classical curve. We just want that this guy is actually a product of P with something else. And actually, we prefer that this is just zero, that this is just one, sorry. So we just want to recover when we send the H bar to zero, the classical curve. Okay, you will see a bit more details about this. So the operators x hat and y hat just satisfy this commutation relation. They are just, they don't commute the operators, while the variables they do. So in here, we just have that the commutator is H bar. And one typical setting is the setting in that we consider a Schrödinger equation. So the P hat just looks like this, some second order, differentiate with respect to x twice, and then minus something that is just the quantization of some rational function. Then you probably all heard about WKB asymptotic expansion. So if you start from something like that, you can actually suppose that the log of the wave function has this expansion, this formal power series expansion. And then the equation will compute for you the S-case recursively. This is the WKB expansion. So the fundamental question that they asked at the beginning of the topological recursion, even before that, is can we construct the operator P hat and the solution just from the classical curve? And then the conjecture coming from topological recursion, this is really from the beginning of topological recursion, is that both the operator and the solution can be constructed from the classical spectral curve using topological recursion. And you will see the idea of how we do this.
Is this operator unique, P hat?
That's a good question. Maybe the conjecture should be more, or the question should be more, is there a canonical way to construct the operator P hat? So you can impose some things and then you can make it unique, but you have choices along the way. You will see a bit what are these choices. So some subtlety that is actually quite important, because otherwise this problem can be, maybe you can think that this is completely trivial. So it's true, you can find a quantization that is really trivial. You just build it in that way. You take any arbitrary S-case that have the right poles, and then an arbitrary thing that kills them. But what we want, and this is really important, is that P hat has a controlled pole structure. And more precisely, we wanted to have the same pole structure as the classical curve. We don't want to have more poles. So in particular, this S-case, they have poles at the ramification points of the curve. And this is not something that we want for the quantum curve. Yes?
You had automatically Hermitian and square, or is it also something that you demand, or is it not important?
I don't know, to be honest. It's not important for the conjecture, because otherwise I would know, but it could be important for other things.
Condition for the L2 metric. The space of L2 functions on X. You know?
Yeah.
So can you say again why you can't just take P0 equals, or P hat equals P equals P of X hat Y hat? Wouldn't that satisfy this equation automatically?
Yes.
They would affect the order H bar.
Yeah, so you will see why it doesn't work in the next slide, I think.
On which space does P hat operate?
Question.
Yeah. US definition, but sorry, I missed the answer.
I think that at this point we are just in formal power series of the question. The space is not one.
Yeah, so far this problem we really only considered as formal power series in H bar. And then for each order of H bar, we have just things that live on the Riemann surface.
It operates as differential operator in x on functions of x, right? That's the
Yes.
idea. But you don't specify which functions of x.
We don't know. No, actually, one of the open questions and also our motivation to finish this work in the formal setting is to really try to do some analysis. Okay, so first subtleties, and maybe this will answer your question, hopefully. We just take our quantum curve, so the operator and the solution. Let's just take it, imagine it of this shape to make it a bit simpler, but things should work in general. Then we just take, of course, I mean, I'm simplifying things a bit for the moment, to be able to take that this is just a formal power series in H bar. We actually need that our spectral curve is of genus 0, but this you will see later. This subtlety, I'm not going to talk about it yet. Then the SKs are just meromorphic functions on the Riemann surface. And then you maybe can observe that the S0, so just the guy that will have an h to the -1, will have to be of this shape. Will have to be of the shape y dx. And it can be multi-valued, and it is actually multi-valued typically.
And z is the same as x in this equation. Right? You use both x and z, but it's the same thing.
Yes, yes, sorry. So, okay, let me talk about what I call the semi-classical limit, and then you will see this subtlety of why you cannot just take the polynomial there. So to go from the quantum curve to the classical curve, this is easy. We just, in principle, we just send x hat to x and y hat to y, but it's a bit more subtle than that, because actually what we just mean is that the operator will annihilate the wave function just on the Riemann surface. So what do I mean by this? Well, you can observe that the action of this on this guy over here, it's just multiplication by y. Okay. And then this gives us that this operator applied to the wave function, just pxy plus corrections in h bar. Okay. So first remark, the differential equation is only satisfied on the plane curve because we need this part to be 0. So we need the curve to be satisfied. And we really need higher order corrections in h bar. Just because this operator, when you make it act in just the beginning of the wave function, which is just this first exponential with h to the -1, it will have already h bar corrections.
So you need them for what purposes? I'm still not following.
Yeah, just to for the thing to be annihilated. So the action of this in this is multiplication by y. That you agree?
Yes.
If you make this, sorry.
What is this lambda as the upper bound of the
Sorry, I'm mixing. You see, I was doubting a lot if to use z, lambda, or x. So in the end, I managed to use all of them at the same time. You just should imagine x.
So you want that exponential of 1 over h bar times this integral should be an exact solution of the Schrödinger equation?
Exactly. So no, sorry. You want the whole wave function to be a solution. And I'm just taking the beginning. I'm just taking the guy with h to the -1 and seeing if that could already be annihilated. And what I'm seeing is that already if you act in the beginning of the wave function with just this operator, you will have already h bar corrections. And then this tells us that for sure there should be higher h bar corrections there. And also the operator will have higher h bar correction.
Why do you have to both correct
Yeah, that's the thing I don't understand.
the solution and the operator?
Yeah.
Why couldn't you just fix the operator once and for all with no H-bar corrections and then just find whatever the solution is?
Yeah, how do you fix the operator? That's the point. So the question is there a nice canonical way to build an operator and the solution? You will see actually that the way to build the solution is very canonical from topological recursion. And then you have to build the operator that will kill this solution just using the classical curve and using the properties of the topological recursion. In general, it's not easy to do this. If you just take, yeah, okay, you could build any operator, but you want really an operator that quantizes your spectral curve. So you want it to have the same pole structure, and you want to have a canonical way to build the solution out of the classical curve. So it's not easy to do that if you want this pole structure. And if you want this canonical way of building the solution out of the classical curve, maybe that's
The pole structure as a function of x.
Yeah, the pole structure of the plane curve. I just mean you will see it better, but I just mean the poles of x and y. So because when you build, you will see that the formula to build the wave function out of topological recursion is just easy, straightforward. You just have a formula to compute this SKs. And this SKs will have in principle just poles at the ramification points, but we don't want poles at the ramification points because the initial spectral curve doesn't have poles at the ramification points, just have certain poles. And the other guys will have poles, but we want to build something that don't have poles, and it's a good quantization.
So it's only going to depend on P. So can I think of it as you're first constructing psi using just P, and now you're looking for P half, so that's the equation. So.
Yeah, exactly. Okay, I hope it's a bit more clear. Of course, you will see more details now, but I should go to a bit of history. So, okay, this conjecture was proved for many particular cases. You will see why this can be useful. And all these cases were genus zero spectral curves. Also because most of the applications of topological recursion come out of genus zero spectral curves, and since people were figuring out everything, so they were interested in computing quantum curves for each particular case. And then in 2017, there was this nice paper in which Bouchard and Eynard, they just solved this conjecture for spectral curves whose Newton polygon has empty interior. And we know that the number of interior points of the Newton polygon bounds the genus. So they solved it essentially for many spectral curves of genus zero, but still genus zero. And then already at the beginning of topological recursion, Marino and Eynard observed that actually to get partition functions that are well behaved, so they are modular, background independent, okay, I hope that makes some sense to you, and actually also holomorphic, they needed to introduce non-perturbative corrections. So they actually observed that if you have spectral curves of higher genus and you don't introduce these non-perturbative corrections, you get something that is not good. Okay, so in 2012, they observed it once again, that only non-perturbative wave functions can obey wood quantum curves with Borot and Eynard. And then now in 2017, he had this idea of how to construct out of topological recursion always an integrable system and their tau functions. That has some relation to the spectral curve, to the quantum curve problem. In 2018, Sidambaran, Bouchard, and Dauphiné, they tried to quantize elliptic curves, but they found, they were trying to do it without introducing the non-perturbative corrections, and they found that the quantum curves that they were finding, they were horrible, they didn't have good properties, they had infinitely many H-bar corrections, so this was not good. Then for some time, people were studying the reverse problem. If you start from a system, what are the properties that it has to satisfy in such a way that you can compute everything out of topological recursion? Maybe this helps you imagine in which cases you can apply this. So if you have lax pairs associated to pan-level equations, for example, you know that it has to have some properties that are called the topological type properties. They were studied by Berger, Boro, and Eynard. In those cases, you can reconstruct the system, the quantum system, and the solutions out of topological recursion. But again, they only did this for genus 0 spectral curves. Okay, so it was only in 2019, and they also did a bit before, in 2016, that Iwaki was able to quantize elliptic curves.
Sorry, why do you say that you have to introduce non-perturbative contributions? I thought the question was about the asymptotic expansion as h bar goes to 0.
Yes, exactly. The problem is that if you just consider asymptotic expansions like that, when the spectral curve has higher genus, you cannot find the good quantum curves with the properties that I said. This is a bit what I will try to introduce during the.
But the property that you gave was just about the small h bar expansion.
Yeah, that's why I said I was hiding some subtleties. In general, you just cannot consider only formal power series, but you need to consider also trans series. So you need to introduce this e to the minus h bar corrections. Then in those cases, we are able to find the spectral curve. So, okay, in 2019, both Olivier Marchal and Nicolas Orantin and Bertrand and myself, we quantized the hyperelliptic curves. So that includes any genus, but it's a specific shape, actually the shape that I was showing you and saying, you can imagine this shape and it's a bit easier. And then what we did last year is we quantized any algebraic curve. So of any rank, not only rank 2, and of any genus. And this is what I will be presenting on the rest of the talk, emphasizing a bit some of the subtleties. But before that, I still want to give some idea on why this is nice and what is the relation, for example, to enumerative geometry. Yes?
You still rely on having a hypersurface realization, or can it also be a determinative graph? Something.
It can be any algebraic curve, really.
Okay.
Like you have a polynomial relation between x and y, and that will work.
But if it's defined as a determinative variety, for example.
That's good.
Okay.
Yes. That's good. It's just what we need is that the base, what we need in this work, we believe it can be lifted, but that the base is of genus 1, of genus 0, sorry.
Okay.
So it's always a covering of CP1. Okay, here I just remind you of the Witten-Kontsevich problem. We just have the Airy curve, and we know that the topological recursion can compute the Witten-Kontsevich star function. So it computes these numbers over here, and this is the quantization. And then there are two different nice generalizations, and then a further one, but these two are in different directions. So one is to consider, instead of this curve that is regular, we consider this curve that is not regular, so it doesn't satisfy some of the properties that I said before. So you need to work out details from topological recursion and everything. But the nice thing is that in 2017, Norbury conjectured which are the enumerative numbers that you have to put here. Actually, which is the cohomology class that you have to put here that will be solved by this topological recursion. And if you want, I don't know if some of you may be interested, this is related, this can be related to Mirzakhani's volumes. This generalizes to Mirzakhani's volumes if you want, which has to do with JT gravity. And here you can also do that generalization, and then we'll have to do with super Riemann surface. But okay, I'm not going to enter into details of that at all. One important remark is that here you see the normal ordering issue. So here you see that the order, so that this is not just replacing things in the spectral curve. If you do that, then this will not compute these numbers. You just have to replace it by this thing that is not so trivial. And then that computes really all the numbers recursively. So this is the good quantization for this problem over here. So you see it's not as trivial as in this case. And then on the other direction, you can also just take the higher rank case corresponding to Witten-Concevic. And then you find here Witten conjectured that you have to put a very complicated cohomology class. And then this will also be computed, but recursively, but this time, but RKDB hierarchy, not by just KDB. This was proved by Fabersad and Joankin. And by the way, this conjecture is some ongoing work with Sinambaran and Zacchetto. And in here, you find that the quantization is just, if you want, the trivial, but you have to prove it. It's not obvious. And then a different generalization that it's more related to our work is just consider elliptic curves. So here we have a parameter T and V, and this is a family of elliptic curves. In that case, well, you have these intersection numbers, and you see the quantum curve is more complicated, yes? Yes, this is really a derivative with respect to T, and this is what I wanted to emphasize. That here, if you apply kind of just the same procedure, if you try to apply the same procedure as here, well, you will need to do something more because you will get things that here vanish and here they don't. And what we did in the work with Bertrand in 2019 is to show that actually these things that don't vanish, they look like infinitely many H-bar corrections, but they can be reobserved in just derivatives with respect to parameters of the spectral curve. This is what happens in this very simple way for the case of pi level 1. So in here, you actually obtain also the over dt. Then since you not only get this, you actually get systems everywhere. You can also eliminate this thing and just get a quantum curve that is an ODE. But this is the first quantization that you find, has nice properties.
So if you change the order in prescription, you're going to mix different genus contributions if the H bar goes to 0. So what you're really asking is that at each genus there's only, so at each order in H bar there's only a single genus that contributes.
Yes, exactly. Yeah, exactly. Okay. Okay, so this is just a summary of the context, and then we will go to the more technical part. So, well, we know that there are many enumerative problems related to topological recursion, also to the spectral curves, because very often we just build a spectral curve from enumerative problems, and also to quantum curves. This was actually one of the motivations at the beginning to prove quantum curves. At the beginning I said, so some slides ago I said, people proved this conjecture in many genus 0 cases. And why were they doing that? Well, in many cases it was to guess or to be closer to prove the topological recursion. Because in general, proving that your problem satisfies topological recursion is not easy. It has many advantages once you've done it, because you have all these nice relations, but it's not easy. So people were computing the quantum curve, sometimes even to guess the spectral curve or to just guess how to prove the topological recursion. Because the quantum curve, in some sense, should be easier to prove. But there are different approaches. So the thing evolved and different approaches arise. So okay, we said that to go from the quantum curve to the spectral curve, it's just taking the semi-classical limit of H bar goes to 0. But what about the other way around? Is there a canonical way to build it? This is the quantization problem that we considered. But there was another quantization problem. So you could just start from here, build the WKB expansion. You know that those satisfy determinantal formulas, and those satisfy loop equations. And topological recursion also gives you loop equations. So this topological type property that I was talking about before, in case you want to have any system and you want to see if you can reproduce everything with topological recursion, then you can use the tools of topological recursion. Well, you have to check this topological type property that basically is telling you that loop equations have a unique solution, and then it will be the solution built by topological recursion. A unique solution, and and a solution that comes from topological recursion. So it has a topological expansion and everything. But really, our approach is different. We just start from spectral curve. We build topological recursion. From topological recursion, we can build the wave function. This is what I was telling you before, that there is a very nice guess for the wave function from the topological recursion. Just build the omega GNs and just take the exponential, you sum over topologies, you put h bar to the Euler characteristic, to the minus Euler characteristic, divide over n factorial, and you take integrals from some base point to z. Yeah, sorry, when I say z, usually I mean a point on the Riemann surface above, and then when I say x, I mean a point downstairs. That's why I interchange them often, because of course they are related. Okay, so this is the guess from topological recursion that is actually very natural, works very well for all the cases that we already know. And then once we have this guess for solution, can we build the quantum curve that annihilates? Well, this is what I will present in the rest of the talk. So this part will be a bit faster and a bit more technical, but at least I hope you can get the idea of how we solve this problem for a very general class of spectral curves. So, okay, I just remind you, topological recursion has some input data, the Riemann surface, X, the meromorphic function from a sigma to CP1, the one form and the B differential. And then we also have to add a symplectic basis of non-contractible cycles. Remember that one of the important things of this work is that we are able to quantize also spectral curves of higher genus. So when the Riemann surface is of higher genus, you just have to consider a basis of non-contractible cycles, A and B, that are like the typical symplectic basis. And yeah, then topological recursion builds for you the omega GNs. And yeah, one little remark is that to fix the B differential, you actually need to fix this basis of non-contractible cycles, because this will fix for you the holomorphic part. This is what I said before, that for genus 0 is always 0. So you don't need this, and things are much easier, and you don't get all these contributions that will be there for higher genus. Okay, so they have nice properties. The omega GNs are symmetric meromorphic, and they have poles at ramification points. And then there is this regularity condition that I already talked about before. So let me continue. So here we consider spectral curves. Here you will see exactly what I mean by the pole structure of the spectral curve. We just consider n distinct points, which are not infinity. And then we consider the Riemann surface that are just the zeros of this polynomial. Well, it can be compactified into a Riemann surface. It has a certain genus. And then the polynomial just looks like this. So if we want it to be monic, we want the highest degree, we want that this guy is 1. So we just have y to the highest degree. Yes, exactly. And then the PLs are just rational functions with possible poles at these points. So they can have a pole at infinity, sure, and they can also have other poles. So these are the poles that we want to allow in our quantization, because that is a good quantization. We don't want to allow poles at other points. And in particular, these points are not the ramification points, which are also important in topological recursion. So there are like two things that if you want to parameterize your spectral curve, the ramification points and the poles. So, okay, we want to allow poles, but not poles at ramification points. And the classical spectral curve is our Riemann surface together with our X that realizes it as a covering. So, okay, we have local coordinates on the base that are just given like that, local coordinates around the poles. And then also local coordinates on the covering on sigma that are just the same as the local coordinates on the base, but of course taking into account what is the ramification profile. So we have just the order at each of these local coordinates in the base, and this will be the ramification profile of every point we have to have, of course, that all this sums to the degree of the covering. And then this will give us the local coordinates in the cover. Then I want to define what I mean by admissible spectral curves.
And further by one thing, at the beginning, you said that you're going to consider only ramification points of degree 2 on sigma, but here you seem to provide a much broader extension.
No, no, sorry if that's disappointing, but one of the technical conditions that we have is that the ramification points are simple. So what is a generalization, and it's an important one, is that we are taking any rank. So we can have sheets, these sheets, not just two, but we only allow two sheets coming together. We don't allow more. We could do that, and that we also have a topological recursion for that. But the very technical steps of the proof need this condition. Yes.
At some of the early stages, you were mentioning also boundary components, but here they're excluded. It's covering space of C2 and
No. So we don't have to mix this is the sigma. This is just a compact Riemann surface. And the guys that had boundary components are the guys of the problem that the topological recursion is solving. So we have to always separate the surfaces of the problem and the surface where all the meromorphic differentials will live. Okay, so here I just consider expansions of omega 0,1 of our one form around every pole, just using our local coordinates. And the coefficient will be called the spectral times or Kp times, because actually in the cases in which we have Kp integrability, they will correspond to the Kp times, that's why. We consider ramification points. This looks a bit technical, but what I just want to say is that these are all ramification points. This is a definition, if you want, of all ramification points. And these are the ramification points that are not infinity. What is going on? So in topological recursion, we actually sum over ramification points that are not infinity. But this was the definition from the beginning of topological recursion. And then people realized that actually sometimes when infinity is ramified, it also contributes. Most of the time it doesn't. But if the infinity contributes, you really need it to quantize properly. That's why I'm separating things here. Just to make it simpler, basically you have to remember that this last condition that we put here that looks very technical, so I don't even will comment too much, is just to make that the infinities that are ramified don't contribute to the formula of topological recursion. Just meaning that if you add them to the sum, they will just give 0. So they are not a problem. Okay, and then there are several technical conditions for us to be able to quantize. So we just have a simple, we just have one ramification point per fiber. Well, we just have the regularity condition, and that's it. Okay, so here I'm just saying that I'm just repeating that we need to choose a symplectic basis to be able to choose the B-differential. And to fix that, we just say that the A periods of the B-differential have to be 0. And this choice of Torelli marking or of symplectic basis is related, if you know a bit this point of view of quantization, is related to a choice of polarization in geometric quantization. And I also want to define here the tuple of filling fractions, but they are just A periods. So these are honest A cycles on the curve, and we just take integrals of the omega 0,1 of those, and those are the filling fractions that have to do with the filling fractions of matrix models. So okay, just I want to briefly give the idea of this quantization procedure. So remember, the omega gns are symmetric. The omega 0,1s have poles at the points that are there. I mean, they have some poles, but remember that we denoted them by P. The omega 0,2 has poles only on the diagonal, double poles on the diagonal. And the higher topologies, they will have poles only at ramification points. So this is important, these three types of different pole structures. Then a nice property of topological recursion that I think is related to the remark that you made before in that other setting is that if we take integrals over certain cycles of omega h n plus 1, this will be the variation with respect to this parameter. In particular, I'm doing it for the filling fractions. So remember, the filling fractions they were defined as a periods of the curve. So they are integrals over a cycles of omega 0, 1. So if we take derivative with respect to them of omega hn, then they will just be, we can just compute them by integrals over the b cycles of omega hn plus 1. This is an important property. And then here, I'm just saying what I said before. I'm just saying that the ramification points at infinity will not contribute for our admissible spectral curves. So let me just skip this and go directly to loop equations. So I just told you what are the pole structures of the topological recursion output. But there are some certain combinations of these omega gns that are especially nice. And these give us the loop equation. Well, you can see this looks a bit scary, but it's just some combinations of omega gns, certain combinations that have to do with the topology. And we have many of those, as many as the rank of the curve. Otherwise, from the rank on these quantities will be 0. And these guys will have very nice properties. And this is the starting point for the quantization. There you can see some particular cases for, you put here 0, 1, you will just get back the rational functions from the spectral curve. If you put 0, 2, well, you get these combinations with 0, 1s and 1, 0, 2. And these functions built like this, they have no poles at ramification points. And this is crucial. So we know that the omega gns have poles at ramification points. These combinations will not have poles at ramification points. And well, here I just wrote the case L equal to 1. So here I said that L can go from 0 to the rank, and then from the rank it will be 0 always. But for the L equal to 1 case, this is the linear loop equation that maybe you heard about in the context of matrix models. Okay, so this is our starting point for quantization. This part we can actually skip. Then we can build the perturbative wave function in the way that I said before in the context slide. Here I just do it for a generic divisor. So we can actually take integrals over a divisor, and this is well defined as long as the sum of the coefficients is equal to 0. And those guys are just formal power series up to these two initial guys that have these exponentially small things. Then we have to also build some other, okay, this part is a bit technical. You can also build, if you just take the n equal to 0 in the wave function, you can also build the partition function. And here the remark is just telling you that wave functions are meant to be solutions of differential equations, and partition functions are meant to play the role of the tau function from the point of view of integrable systems.
We're supposed to integrate this omega h0 inside the exponential.
Here you don't integrate because you have the n equal to 0.
Oh, it's
And here
it's a 0 form. Okay.
Exactly. Yes, yes. And then here you have n integrals. Okay, just integrate for each of the variables. Okay. Then from the loop equation, so from this nice combination of omega gns that have the nice property that they don't have ramification points, you can actually build the KZ equations. Okay, they look a bit scary because also they include these quantities that I didn't comment too much on. But the point is that this is kind of a differential equation. So here you have the derivative, and this is actually a differential system. Here you have this derivative. Here these guys also can be seen somehow as derivatives. And well, this guy is built out of those quantities in some way or another. And what we want to do later is to handle these guys. These are the guys that in G0 are very easy to handle, and in the end they are mostly 0. And in general, they will be complicated, and then they bring us many technicalities. Then there is also this term that when you take a divisor that has the property that alpha I is 1 or -1, then it will just be 0, and it will be a bit simpler. That's what we'll do. So we will just take the simpler case, and we will take a particular divisor. So we just
the goal is to read off the differential operator key from this differential.
exactly. So we built these case equations. For the moment, they are parts that are really ugly, and I want to say the idea a bit on how we arrive to the quantum curve from that. Exactly. So to do that, we have to take a particular divisor. So it just here in this case, we just take z minus infinity, one of the preimages of infinity, and we just have to regularize our equation, our function and our equation, because infinity can bring some problems. So just need to subtract some part at some other and modify the equation accordingly. So this just comes from the previous one by doing this regularization. And the observation is that in the right-hand side, you see these residue calculations, so just integrals. These can be rewritten using generalized integrals, so some linear operators. And these linear operators are expected to correspond to derivatives with respect to the moduli of the spectral curve. And this is what happens exactly for rank 2. Okay. In general, there are several subtleties why we didn't do this. So we think that it can be improved, and in general, this connection can be made, but there are many defining the that is just side. And we call this the important things is, and like this, we just avoid the technicality of defining these guys on the whole space of differentials. So here I explain a bit how to do it. So we have 3 different types of cycles, the ones related to the poles, and in such a way that they are just corresponding to residues when applied to the differentials. So they are just circles around the poles to a certain degree. So just need to multiply by this guy over here. Then we also consider chains from a certain point to a pole. And then we consider the honest the honest cycles. And well, like that, we build the evaluation of these symbols using these operations over there. Yeah, sorry that this part is a bit fast, but hopefully you are getting the idea. So in the end, we just build some operators that act on these symbols like this, and that we can evaluate using just what I explained very quickly. And then this gives us a quantum curve. I mean, not a quantum curve yet. This gives us another version of the KZ equation, in which we just replaced the right-hand side that was really awful by this linear operator acting on this. That is not much better, but it's towards what we want to do. So in the degree 2 case, just to scare you a bit less, these operators just correspond to derivatives with respect to the moduli. I just want to show briefly how that looks. So in that case, these case equations just look like that. In the degree 2 case, this is and just nominal degree 2 from its case equation just looks like this. It has this that this just write it in terms of the moduli of the spectral curve. So in terms of derivatives with to the moduli. They're derivative with respect to the poles and derivative with respect to the kp times. And remark, important remark, in the genus 0 case, so you can see why it's much simpler, this L operator, so this very complicated part, is just 0 in the genus 0 case. So here I just give the example of the Airy curve and of the Elba curve. I will try to finish. Quickly. So for the Airy curve, we just have this case over here. The L is equal to 0, and we just have this system, and you can recover the Airy equation out of that if you do the specialization of one of the 2 points of the divisor will be infinity. In the hyperelliptic case, you just get this curve, and you can do the same, and you can bring it to what I showed before. And yeah, what I wanted to remark here is that here the L is 0, and here the L is simply d over dt, as I showed at the beginning. Okay, so just why do I have to introduce these non-perturbative corrections? I will just give this last idea and we can finish. The monodromies of these perturbative wave functions are really bad. They are not really even functions. So these guys are not invariant when Z goes around the cycle in a higher genus spectral curve. And in particular, when you go around the B cycle, you have things that are not even monodromies. They have really bad behavior. So you see when you go around an A cycle, you have this nice monodromy that is to be expected. When you go around another type of cycle as well, but when you go around the B cycles, you have something really ugly that has to do with shifting the filling fractions. Just have to remember that. And we just add these non-perturbative corrections in such a way that we can cure this big problem of the bad monodromies and have nice monodromies. And this helps us find the quantum terms. So we just sum over the lattice. So we just sum over the fundamental group of the spectral curve if you subtract also the poles. And then these guys will satisfy the same KZ equations, just because the KZ equations don't depend on the cover, but they depend on the points on the base. And the goal is to build solutions to the same KZ equations that we built, but with better monodromies. And what we do is this kind of discrete Fourier transform in which we just take these sums over the lattice. So we just sum over all possible B cycles. And we introduce things that keep track of how many B cycles we put. And we have to shift, because remember that this was the price to pay when you go around the B cycle. But okay, actually, because of some technicalities, you cannot take this nice discrete Fourier transform ordering that I showed here, but you just have to take another order of the monomials. Okay, this is something technical, but it's fine. And here we just use things that are like the Riemann zeta function, so and their derivatives. And with those guys, we can just build the non-perturbative wave functions. If we build the non-perturbative wave functions with these theta functions and their derivatives, we arrive to wave functions that are built out of the perturbative ones, and they have nice monodromies. But you see that things are much more technical because we have to work with this trans-series, and we have to show everything order by order in the trans-series. So let me just show the last result. So here we built the lag system. So we just start from the KZ equations of before. We just transform those ugly parts in those linear operators. We build the non-perturbative solutions to the same KZ equations. And then once we have the nice non-perturbative solutions that have the nice monodromies, we can build the lag system. So we just build this lag system. We also build the auxiliary equations to the equation that we find directly. It has this shape over here. And the L and the I are H bar trans-series functions that are rational functions with no poles at the critical values. So they have the right behavior that we wanted from the beginning. Okay, and Sorry, this looks a bit scary. Just to say they have only poles at the poles of the spectral curve, and they may also have some poles at the zeros of the Röntgen, but these are just apparent singularities. So they are not important. And then we can find 4 different gauge transformations that have different advantages. In some, you can read the spectral curve easily. In some, you can read the quantum curve easily, and that is interesting. And in some, you can also get rid of these apparent singularities and get really the pole structure that you wanted at the beginning. So, okay, here I will skip the link with isomorphic systems. And here you see some of the future work to do. So some of the things that we would like to do is explore some abilities, some exact WKB, and basically, can we do analysis with what we did so far? And can we see the non-perturbative partition function as a tau function in general? Can we actually change the basis of A and B cycles, and how does the connection then change? Well, those are all things for the future. We could also try to get rid of admissibility conditions because we think it's possible. Just that our technique of proof is really, really technical. So right now we are working on trying to find a more conceptual proof of the quantum curve because you saw that it can be quite technical. So yeah, thank you for your attention.
To summarize, I'm still not exactly sure where the logic starts. So at some point in the middle of the talk, you said, and this is sort of our best guess for the wave function. Yeah. And so my understanding is you start with P, you apply, again, you need, I guess, this omega 0, 1 in the pi differential. And then you have a machine that works, sort of topological recursion. And now that gives you some perturbative wave function, but you think that there should be something, some solution of the differential equation behind that. That's why you call that your best guess for a wave function?
Yes. Yes, if you want just, and there are more conceptual reasons, but if you want a very easy one, that is exactly what works for many classical cases, like in the Witten-Koncevich case, you have the Airy differential equation. That is exactly the WKB expansion. You can observe that the easiest WKB expansion is gives you exactly the same recursion as the topological recursion, and that the WKB expansion is built out of the topological recursion in this very precise way. And then this was proved for many. I mean, this was conjectured like that because it was working very well for the Airy case and because of other conceptual reasons. And then it was proved for many cases. So in the end, it was like, okay, this is the way to go. And the problem was that for higher genus curves, you also need these trans-series corrections that I had to do very fast because it's a bit technical. But so that was kind of not part of the initial conjecture.
But for the integrability case, you don't need this trans-series, or you have to, because even for integrability case.
Yes, you also need it. If you have higher genus, you always need it.
Starting with genus 1.
Yes.
Can you think about branch cuts as being a horizontal slice of tangent? And as soon as you have more than one branch cut, you have tunneling effects between the different minima of the potential,
Yeah.
which is why you need to include these non-perturbative corrections.
Yeah, exactly. That could be a nice heuristic or conceptual explanation.
Maybe one out of just curiosity, if you take a very simple curve, like how many possible y squared minus x squared, do you enumerate anything with this machine, or does it give you
So you want to consider y squared equals x squared?
Yeah, how many possibilities that would be?
Yeah, that one is a problem because you don't have ramification points that are not infinity. if you, I mean, you can parameterize it by x equal to z and y equal to z. Then you don't have ramification points and you will have zero contributions. So you cannot take any spectral curve. Usually you want things, I mean, in the easiest setting, you want things that behave as a square root, like in the Airy case. That is kind of the model for every classical problem. That's why people discovered that you can express any topological recursion problem in terms of these building blocks of intersection numbers. And then people explored other behaviors. They explored high ramifications, like when you have x equal to z to r, or also when you have non-regular behaviors, like in the case I presented on the right. In that case, you have y equal to 1 over z. So you have a pole, a simple pole of y around the ramification point. That is not allowed in the usual definition, but you can allow it, and you also find other nice, interesting geometry. So it's a bit, so far it worked a bit like that. Like people were exploring, like you now, does this work? Okay, this gives nothing. And does this work? And people were guessing. It's more like we know how topological recursion transforms when you transform the spectral curve within families. So you can guess if you have your enumerative problem that you want to solve, you can guess easily if you master a bit the rules for the spectral curves. But there is not a systematic way to say like, okay, we have studied all spectral curves. It's
Yeah, I was just going to do that. So we'll have lunch with, I think I'll agree to stay for lunch.
Yep.
And then we can continue questions.
Yep, sure.
Okay, so let's just thank you.
Yeah.